So back for another episode of the Money Button documentation series, where we are documenting not just Money Button, but also the sort of basic technical background to understand Bitcoin, to be able to make advanced applications on Bitcoin. We're covering all this information primarily for educational purposes, just so that people can understand stuff and you can use the library and so on. Of course, Money Button itself is part of the goal here is to make it so that you don't actually have to know most of these things to be able to make advanced applications. But we're covering it anyway because there is sort of a need for this type of information to be available for people. So today we're going to talk about transactions and blocks. And this is a presentation I originally created, I think way back in 2014. I have some records that I gave it in 2015. I think I originally created it in late 2014. So it's quite old, actually. And I haven't given this presentation in a long time. So I sort of updated it slightly, but it's pretty much the same as it was back then. And the idea of this presentation is covering all of the sort of guts of what is inside of a Bitcoin transaction and what is inside of a block, and just covering all of those details. So it's extremely technical, and we've been building up to this over time because we've now given basically the other types of technical information that people need to understand what we're about to discuss. I will say, though, that I've given this presentation sort of as is to engineers, and they can normally understand what I'm saying without necessarily having seen all of the other material first. But it's super technical. There's no demos of code in this presentation, so this is just covering just technical information. And then so we'll have other examples in the future of like how to actually build a transaction and things like that. So if you guys are ready, I'm just going to get started. And as usual, let me know if something goes wrong because I won't be able to tell otherwise.
Okay.
Okay, so transactions and blocks in bitwise detail. So basically an overview is we'll talk about a bit of a summary about what are transactions and blocks, and then talk about a number of different ways to format numbers, and then talk about public keys, signatures, and addresses as seen on the blockchain, and then what are inputs and outputs, and then once we have all that stuff, we can talk about what a transaction is, and then finally talk about what blocks are in complete detail. So first of all, there's this wonderful photo of what is a Bitcoin transaction from the Bitcoin white paper. And this is a very good overview that shows you the basic idea here of what is Bitcoin doing when you send money. So we have three different transactions here, where owner 1 sends to owner 2, owner 2 sends to owner 3 then sends to some other person who's not listed here. And the idea here is that for a given transaction, like looking at the one in the middle there, what we see is we have owner 2's public key, and they, in order to spend this, okay, so this is owner 1 sending to owner 2. So it goes to owner 2's public key, and they have to hash the entire previous transaction, which goes inside of it, and then add the signature to it. And so that is a Bitcoin. And if you read the white paper, it actually specifically says this is what a Bitcoin is. And this is the idea that what you're doing is, like if I were to say send Mige a transaction, I would take my existing coin and then I would just add to it Mige's public key, and then I would sign it and then give it to Mige. And then Mige, if you want to send to Ohe, you would then do the same thing. You just take that chunk of data and you sign it, and then, or you add Ohe's public key to it and then sign it. So that's it. And so it's a chain of transfers of ownership. Now in this other photo here, I have examples of 4 different transactions where you're sending 1 Satoshi. So if you interpret that graphic literally, it's what it would look like if everybody sent 1 Satoshi at a time. And so this would be an example of what it would look like to send 4 Satoshis. You'd have to send 4 different transactions if you sent 1 coin at a time. But of course, gosh, it would be convenient if instead of sending one at a time, we could merge them so that you can send multiple different coins in the same transaction so that you don't have to sign so many things all the time. And then if we could do that, it would be convenient if we could actually have multiple different values in inputs and outputs of transactions. So rather than simply sign individual coins over, we sign over quantities in different inputs and outputs. So it allows you to spend from other coins and then to other people in different amounts. And so this, roughly speaking, is what a Bitcoin transaction looks like, where you input values and then you output values in any quantity and then in any combination. Now, here's another way of looking at what a Bitcoin transaction is. This is sort of a detailed sort of bitwise overview. I'll sort of quickly cover it. I do highly recommend looking at this for anybody that ever builds a wallet. This is a wonderful chart created by Alan Rayner quite a long time ago. I think it goes back to 2011 or so. Alan Rayner was the founder of Armory, which was an early Bitcoin wallet. And what you see in this chart here is you see things like the transaction has a number of different inputs and outputs inside of it. And the inputs spend from other places. And so it starts with a version number. This is, it lists 4 bytes there. That's how long it is. And then each input there, you see 3 inputs in a row, and then you see 2 outputs. And then it describes what these look like when you see these things. And it says things like, you know, the first input has some numbers there, which is the output hash that it's referring to. And it has like the output index number, and then it has the length of the script, and then a script, and then a sequence number. So the different parts there are, you know, the output hash, TX output index number, script length, script, and then sequence number. And that's in the input. The output has something different. It has its own script, and it has a value in there. So it starts with a value, which is 8 bytes, and then the length of a script and a script. And so outputs are a bit simpler. So we'll talk about this in more detail as we go through this, because basically this whole talk is about what is inside here. What are these things in here? And then the very final piece on sort of the top right of this chart, you can see the lock time. And the lock time is a 4-byte value that indicates that the transaction will be valid at a certain block. So normally you do not specify anything in the lock time, but you can make it so that your transaction will be valid in the future by putting something inside the lock time. So that's a very rough overview of what the data is in there. Now that we have some idea what is a transaction, blocks basically are just groups of transactions with an additional hash that has proof of work. So it is a group of transactions with a proof of work hash, and each block links to the previous block, and each transaction links to earlier transactions. And so that gives you just a high-level overview of what is the structure of the blockchain. It's a blockchain because it's a chain of them. Each block links to the previous one. And the transactions actually have their own chains. So the transactions link to earlier transactions, which can be in the same block or can be in an earlier block. So the transactions actually don't know which block they're in, other than the possibility of having an in lock time on the transaction, in which case it's valid after a certain block number. But that's, other than that, there's no other reference to what block a transaction is in. So transactions sort of chain themselves into, it's not really a chain, it's like a weird structure with multiple inputs and outputs. Blocks are simple, they're just a chain. It's a group of transactions that have a simple link to the previous block. So that's an overview of the structure. Now, and then guys, if you have questions, what we'll do is, if it's important, just feel free to either comment or ask a question as we go here. But otherwise, maybe we'll just save it to the end if it can be saved, just because it's so much. I don't know what other way to do it, but basically, just if it's important, let me know. Otherwise, I'll just keep going and keep covering all this material, because there's quite a lot in this presentation. Okay, so now here's an example of a number of different number formats that exist. Bigendian, Littleendian. So Bigendian means start with the most significant. digit. Littleendian means start with the least significant. Sign magnitude means it's a way of representing positive and negative numbers. Two's complement is a different way to represent positive and negative numbers. Fixed point means you have a sort of a fixed number of decimal places. Floating point means that the number of decimal places can change, or to put it differently, the precision is the same, but the exponent can vary. You can have numbers formatted as a string, and of course you can have different sizes like 8-bit, 16-bit, 32-bit, 64-bit, 256-bit. You can even have variable sizes. There are many different ways to write a variable size. And so the question is, which of these number formats does Bitcoin use? And it's a joke because actually Bitcoin uses every single one of them. So unfortunately, if you want to understand all of the different numbers that are inside of a Bitcoin transaction, you need to understand, let's see, how many is that? That is 1, 2, 3, 4, 5, 6, 7. It is 14. And of course, you can combine, mix and match these in different ways. So it's actually just many, many, many different ways of formatting numbers inside of a Bitcoin transaction. So it uses every single one of these. And so we'll cover these one after the other here. So first of all, for people who aren't already familiar, there's a difference between writing down a number as Bigendian or Littleendian. So Bigendian there on the left means this is the normal way you would write a number. It starts with the most significant digit, and I've written the number 1,000 several different ways. So you can see the number 1,000 written the way you normally would in decimal. You can see the same number in hex, where we're using 16 digits, which includes a few letters, A, B, C, D, E, F. So that one looks like 3E8. You can see it written as decimal bytes. So if I had 2 bytes to represent that in Bigendian, that's how I would write it down. So that's actually base 256 is what decimal bytes are, where each individual byte is in base 10. Then I show hex bytes, and the difference between hex and hex bytes is that hex bytes always comes in pairs. So I have to use 2 digits to represent 3 because I have to put it in pairs. And then finally at the bottom there I have this number written in a Bigendian binary format, where each each byte is written in binary. Okay, now on the right-hand side, I have the same number written in Littleendian, which is the backwards of what you would expect. So this is the number 1,000, but it starts with a 0 because the most significant digit is actually on the right. And so the hex ends up being in reverse. So it's 8E3 instead of 3E8. The decimal bytes are reversed, but inside it's still sort of the same. The hex bytes are interesting because you can start to see where it matters that I'm reversing them as bytes rather than as characters. So it's E803. So it looks different than hex. So, and that's significant. I mean, it makes a big difference which format you're writing them in. And basically always inside of our library, it's always in hex bytes. So that's always what we mean. It always comes in pairs, and you basically never see it written in hex. That's sort of an odd number of digits. And then finally, I have the same number written in binary at the very bottom there. Okay, so there's another thing to be aware of, which is how to represent sign, which is whether you have a positive number or a negative number. Because of course in a computer, you just have a bunch of ones and zeros, and so you have to come up with some way to represent what is a sign. Now, the obvious way to do this, or at least it seems obvious and intuitive to me, is to just take one of the bits and say 0 means positive and 1 means negative. And if you take the most significant bit and do that, that's called sign magnitude format. And this is a not actually all that common way of representing numbers. You would think that this would be common, but it's not really that common. But in any case, I show some examples there of like the number -1. What does that look like if we write it in sign magnitude form? Well, the first interesting one is the decimal bytes, where it's 128,001 on the left side there. That's 4 bytes, and it starts with 128 because, well, the most significant bit is flipped. And so if I write that down in decimal, it ends up being the number 128. Whereas if I write it in bytes, it starts with an 8. And so, or sorry, in hex bytes, it starts with an 8. And then if I write it in binary, that's the easiest one to understand, actually. You can see how the most significant bit on the left there is 1. That is the sign bit. And then the least significant bit is just the number 1, and that's what's telling us it is the number 1, and everything else is a 0. So that's how you write down -1 in signed magnitude form. On the right side there's 2's complement. Now, the irritating thing about sort of, this isn't really Bitcoin, this is kind of x86 machine. So many of us are using we're using x86 machines or something sort of derived from that. x86 uses Littleendian 2's complement for numbers. So when you have like a negative number, it is always Littleendian, which is backwards from what you expect, and it's 2's complement, which is not signed magnitude. So this is just, there's a formula for writing down sort of in binary, what is the 2's complement of a number. So how to write it down as 1s and 0s basically. And it's that formula, I think there's a slight typo in this slide. It's actually supposed to be 2 to the n minus x. And the n is the number of bits. So you see some examples there. And so this is the number -1, but it ends up being like in binary at the bottom. It's easiest to understand. It's all 1s. And that is the number -1 formatted as 2's complement, Bigendian. Now I show the same example here in Littleendian because that's how you would actually see it. So the number -1 is not that enlightening. But the number on the right there is how you would normally see that in a computer. Like if you have a C or C++ program, and then you print out the bytes and then try to print it out in binary, you would get that. It would be a bunch of 1s. So this shows up in Bitcoin in different places because basically sometimes you want the maximum unsigned integer, or you cast -1 to a unsigned integer, and this is what you get. You get a bunch of 1s. You get something that looks like this. So this happens, for instance, when you have a maximum sequence number, this is what it looks like. So here are just a couple of examples so that people can see what this looks like in this particular case. So on the left there, I've written the number in the usual way. So 5, 5, 5, -5, -5, -6, -6. And then on the right, I've just formatted it in a couple of different ways. So it's Littleendian, which is how you would normally see it on an x86 machine or inside Bitcoin, sort of normally. So we see the most significant, so I'll start with the first one. So it says like 05000000. That is the number 5, Littleendian in 4 bytes, and it's unsigned. Now, the thing on the left is the 5 because that is the, let's see here, that is the least significant digit. And I guess it sort of gets interesting when you see like the 4th one down. It says 05000080. That's because it's Littleendian sign magnitude. So the most significant bit is flipped, which is actually on the right side. And so it looks like 80, but it's on the right, and that's the most significant. And then you see -5 and 2's complement, and it just looks completely different because of that weird formula 2n minus 1 or whatever it is. And then there are a couple other examples there. So that just gives you an idea of what this actually looks like when you format one of these numbers in this particular way. Either it's 4 bytes Littleendian, and then either sign magnitude or 2's complement.
And
now,
just,
yeah, go ahead.
Sorry, a small comment. Like at least when you see that, it's like it looks completely weird, and you see like why they invented this, right? And when you see like this in the implementation of the processor, actually it makes sense. It's like it makes the processor simpler. It makes the programming harder, but the processor simpler, basically, and faster.
Yeah. So
like there is a reason for all these weird ways to represent numbers. Well, just that comment. Like it's not something random. It actually makes sense when you see how the processor works, basically.
Yeah, that's a great point. So we care about this for that reason. Like, you would wish that what we actually want out of a processor is that they're fast, basically, and that's really what they're doing is they're doing it in an efficient way. So normally the sort of the programmer doesn't really care about this unless you care about encoding things in sort of 1 byte at a time. So normally you don't have to worry about this, but yeah, that's the reason, is that it's really a processor architecture thing. And high-level languages like C or C++ actually don't they mostly abstract that away from you until you try to get down and actually deal with individual bytes, and then it matters. And so the reason why we have this in Bitcoin is because that's how processors worked. So because the x86 machines did it that way, that now shows up in the Bitcoin protocol, because if you just start printing out bytes, you get things naturally in the way that it's done on the sort of the processor architecture that you're using. And so we're stuck with these sort of Littleendian numbers in some ways, and Bigendians and others for different reasons. And so we'll get to that shortly, but yeah, that's the reason. So there's another type of number that shows up in Bitcoin, sometimes called Varint, sometimes called compact size, which is a way to represent usually a length of data where the number is not a fixed number of bytes. So the number can vary. And so this is basically useful if you're trying to be efficient, where you want to be able to represent large numbers, but where you don't always want to use, say, 16 bytes or something like that when you don't need to. So it's an efficient way to encode numbers. I show there's an example there where, like, imagine you have the number, that's just the number, well, it depends on whether it's Bigendian or Littleendian. I'm not sure what I'm writing there, but let's assume that's Bigendian. That's the number 1. Then it's like you're wasting 3 bytes there, because the number 1 can be fit in a single byte. So what if there were a way to represent, basically have a variable length for numbers? And the way this works is we have a header byte that basically says what is the length of the number itself, followed by either 0 bytes, in which case the first byte is the number, assuming it's small enough, or 2 bytes, in which case the following 2 bytes are interpreted as a Littleendian unsigned number, or 4 bytes, in which case it's followed by 4 bytes of Littleendian, or 8 bytes, in which case it's 8 bytes of Littleendian. So basically we can have basically up to an 8-byte number, which is a huge number. I don't know what it is here. I think actually I've got one example written here. So here are some var-ints, and using var-int, we have the number of, you can see it on the left there, that it allows us to write down a number using a variable number of bytes. And so way at the bottom, we can see what does a big number look like, and that one's quite large there. So we can encode very, very large numbers this way, all the way up to 8 bytes. So that just shows you what that looks like. And this is used inside Bitcoin transactions. And this particular format, as far as I'm aware, is custom to Bitcoin. This is not some computer architecture thing. This is just Satoshi needed a variable sized number. And so he just invented this custom variable sized number. Okay, so we've covered many of them, but moving on here, we've discussed this in earlier videos, big numbers. So the largest numbers you can do in C++, which is what Bitcoin was originally programmed, and to this day, of course, the node software is still in C++, you can basically go up to 8 bytes. But we need 32-byte numbers, because we need the ability to do 256-bit elliptic curve mathematics, and so therefore we need 32-byte numbers. And we also have things like hash functions, which are often interpreted as a 256-bit number. So even though that has nothing to do with elliptic curves, when we compare the proof of work of one block to another one, we actually interpret that as a number, and we want to look for lower numbers. Sometimes when we see big numbers, they are either Bigendian or they are Littleendian, depending on context. So unfortunately, it can be either one, and that's why you really have to understand these things if you get into the details, because it depends. Sometimes it's Bigendian, sometimes it's Littleendian. And then also sometimes they're unsigned and sometimes they're signed magnitude. And then I have a little comment there that as of when I originally created this presentation, I was not aware, and still and to this day not aware, of any example of 2's complement in big numbers in Bitcoin. If you ever see a negative number, it is actually a signed magnitude big number. And then there's an example at the bottom of just an example big number that is in, which is the order of the group of SCCP-256K1. It is basically the number of private keys is what that really is. And it's written in hex, and that is a large number. It is 256 bits. Okay, so there's yet another type of number that we see in Bitcoin called script num. So we'll cover script itself in a whole other presentation because it's very interesting and it deserves its own presentation. But just know that there is a programming language built into Bitcoin, and it's a Forth-like programming language that has a stack. In fact, it also has an alt stack. There's no heap, so you can push and pop things from the stack, and you can push and pop numbers, and you can add numbers and subtract numbers, and now you can multiply numbers and stuff. So these can be normally 4 bytes, but they can overflow. So if you add 2 numbers together and you add like the maximum 4-byte number plus the maximum 4-byte number, you get something that's 5 bytes long. And so they can overflow. So they can end up becoming longer. And I believe they can become as long as 8 bytes. So this is just a unique form. This is not a 4-byte number, and it's not varint either. It's like a unique way of representing numbers that is specific to script, that I think is just another case of a custom number format in Bitcoin used in script. Okay, there's another way to represent numbers that we see in Bitcoin, which is a fixed point. So far we've been talking about integers, which are either positive or negative. We haven't talked about fractions. How do you write a fraction? Well, one way to do it is with a fixed point number. And this is where you basically have a certain number of digits always. And this is how we see Bitcoins written, because 1 Satoshi is 1/100 millionth of a Bitcoin. And we always use fixed point numbers for this. And this matters because of the way the arithmetic work is actually different than floating points. So that's where we see fixed points. And let's see here. Do I have Satoshi's always unsigned integers? So inside Bitcoin, it's actually just a number. But when we draw them out, it ends up looking like a fixed point number. So that's a number of Bitcoins is something that uses fixed point. And 10 to the minus 9 is not a valid Bitcoin amount. 10 to the minus 8 is the smallest quantity of Bitcoin because that is 1 Satoshi. So we have fixed points. We also have floating points. So this allows you to have a number where you have sort of any number of decimal places. So instead of being limited to, say, 8 decimal places, you can have any number of decimal places. And so it just works in a completely different way. And you have, I've written there on the 3rd line, you can see it says -1 SC BQ. I think that might be formatted wrongly, but there are a couple of properties. You basically have a sign bit. You have the sort of the number bit, and then you have the exponent. And so I've written some examples as a string on the 4th line there. So 6e minus 45 means 6 times 10 to the minus 45. And if I remember correctly, the way the standard works that you see in languages like C++, it's IEEE 754, it's actually base 2 exponent, if I remember correctly. If anybody, Mega, if you happen to know this, or you normally wouldn't care about this. It's another one of those things where almost all of the time this is abstracted away and you don't care unless you care about literally implementing floating point numbers yourself or something like that. So I think it's actually implemented internally as base 2, like a 2 to the number. But yes, you always go ahead.
It's base 2. I'm not sure.
Okay, so but we always write them down as base 10. So we can always see them as like on the last 2 lines there, minus 6.123 times 10 to the 90. And so we can go all the way out to, it's a negative number with 90 decimal places basically, with 4 digits of precision. And I've got it written as either a Bigendian double or a Littleendian double. And it's a double, so it's 8 bytes. And that's just what it looks like. And the only way to get that precisely is to like actually implement IEEE 754, and it comes out like that. And that's just what it looks like. And I think you can look at, if you look at this up on the internet and go find you can see what the different bits are and stuff like that inside those numbers. But that just shows you, this is just yet another way to represent floating point numbers. The standard IEEE 754, I don't think that's actually used in Bitcoin. We have a different thing used in Bitcoin, which is called bits, which is a floating point number, which is representing the difficulty of mining. And so that's actually a custom floating point number. So coming back to all this stuff again, here are all these different ways to format numbers. And unfortunately, if you want to understand what's in a Bitcoin transaction, you actually have to understand every single one of these. If not in a Bitcoin transaction, then in the protocols around it, such as displaying numbers and interpreting them and all this stuff. Every single one of these shows up somewhere. So just roughly, Bigendian, we have this in public keys and signatures. Littleendian are hashes. So when we interpret the hash of a block, we actually use it as a Littleendian big number. Sign magnitude occurs inside of things like signatures. They can technically be minus. And so those are sign magnitude numbers. We see 2's complement scattered throughout. Basically, anytime we have an integer inside a transaction. We have fixed point because that's how we write down what a Bitcoin is, a quantity of Bitcoin. We have floating points because the difficulty of mining is a floating point number. We have strings, of course, because we display all these things. We have RPC interfaces and APIs and all that stuff that use strings in various places. We have all sorts of different sizes of numbers, 8-bit, 16-bit, 32-bit, 64-bit, 256-bit, all occur in different places, inside opcodes, inside variable size numbers and things like that. And then there are at least 2 different custom variable sizes. One is the script num, and the other is the Varmint. So literally every single one of these are used. And so hopefully these concepts, it's not like you have to memorize these, but so that you're aware at when you deal with any of this stuff, hopefully you don't deal with it. But if you do, you're just aware that there are all these different ways to format numbers inside of a transaction and the APIs and stuff. Okay, so now with all that stuff said, we'll move on. We've got the number format stuff out of the way. So now we can understand what a public key is. So we've already had this whole other presentation on like the elliptic curve mathematics and all that. So mathematically, a public key is a point on the SECP 256K1 elliptic curve. And a private key is a big number multiplied by G, which is the base point of the curve. That's what it is mathematically. When we write down a public key, because you have to put them inside of a transaction, we need to be able to write them down somehow. And so the obvious way to do this would just be a 32-byte number for the X value and a 32-byte number for the Y value. But actually that takes up a needlessly large amount of space because there's actually another way to write them down, which is in compressed format, which is where you write down whether Y is odd or not, and then the X value. And that way it's only 33 bytes instead of 64. So it saves a good deal of space. So this is a DER formatted public key is written this way. It's called compressed. And this is usually, basically every modern wallet does it this way. But early on in Bitcoin, actually the original wallets did it differently. And so it starts with a 4 to indicate that it's uncompressed, followed by an X and a Y value. And so that's just how it was originally. So these occur in the blockchain. But today, every single wallet does it in a compressed way because it's strictly better. It just saves space, and you have to pay for every single byte in a transaction. So you want to save space, and these do go inside transactions. There are other ways to prefix the number. There's just an interesting fact in the history of Bitcoin. You can follow that link there on SourceForge. There's some discussion about other ways public keys are formatted in the blockchain because Bitcoin used OpenSSL originally. And so all of these standards come from OpenSSL. So you have different reasons why there are these different numbers in Bitcoin. Some of it comes from the architecture of x86 machines. That's why you have like Littleendian ints and stuff like that. You have some of it comes from OpenSSL. So all of the crypto stuff used OpenSSL. So these are just default ways to encode public keys. That's why it looks like that. That's just what OpenSSL did. And so OpenSSL was used in Bitcoin. That's it. Then you also had Satoshi had to invent some new formats. And so then you have the other things like Varmint and so on that are just brand new, specifically for Bitcoin. So anyway, that's all those things. Now we need to put signatures inside transactions as well. So again, we've already covered what a signature is in detail. We've covered the math of it and everything with elliptic curves. A ECDSA signature consists of 2 values, an R and an S. Both of them are 256-bit numbers. There's 2 different ways that we see how to format signatures. We had a presentation on this just yesterday. You can have a compact signature, which would be the obvious way to do it, which is just 2 values. And this is usually encoded in base 64 if you see this with the Bitcoin message signing, and that's exactly what we covered yesterday, and we'll link to that. But actually, that's not in the blockchain, and the way that you see it in the blockchain is in DER format, again, because that's just what OpenSSL used. So what DER format looks like is you start with a DER signature followed by a hash type. So the DER signature is right there, HL, RH, RL, R, SH, SLS. And again, we covered this in the presentation yesterday, so we'll provide a link and people can, if you want to not have this glossed over. We discussed it in detail yesterday. But they're sign magnitude, variable sized big integers that are never negative. It matters because the sign magnitude can cause there to be an extra byte sometimes if the most significant bit is set. Because it's sign magnitude and it's not negative, you actually need another byte. So it's just kind of complicated. And that's just what OpenSSL did. And so there are a number of different header bytes and length bytes. Now, the hash type is something we'll talk about in a whole other presentation because it's really interesting that there are different ways to hash a transaction. I'll just say them for the sake of anybody like listening. Sig hash all, sig hash none, sig hash single, sig hash anyone can pay. This is when you create a signature, you have to hash the transaction, and there are different ways to hash it. And the hash will cover different parts of the transaction depending on what you're doing. Sig hash all is the standard one, which means you signed the entire transaction basically. The other ones are special cases that you can use for all sorts of interesting things, which we'll cover in a different presentation. But at the bottom there, you see what are the different bytes there. And we have, it always starts with the hex value of a 30, whatever that number is in hex, and then a number of bytes, including the R and the S, and then followed by a hash type. And so that's what you actually see in a signature in a blockchain. Looks like that thing at the bottom there, formatted that way. Now, another thing we see in the blockchain are opcodes inside script. So, and I think I already said this, but we'll have a whole other presentation on what script is because it's extremely interesting. And this is going to be the world's simplest overview of script, which is, well, it's got opcodes in there in data, and this is what they look like. So here are some of the opcodes. There are something like 175 or so of them in total. Here are some of them. And let's see, we've got things like op false. That just pushes 0 to the stack. We've got a number of push data. The only interesting thing I'll say about push data is that from the very beginning, we had push data 4, which says the following 4 bytes are used to push data to indicate the length of the data, meaning you could push up to 4 gigabytes of data in a single transaction in the original protocol going back to January 2009. So all this drama that people had about the block size, well, there's only one reason why you would need op push data 4, which is if it was the idea originally to put huge amounts of data on the blockchain. That's clearly anybody that reads script can see that. Okay, anyway, moving on. I've just listed the first several of them here. We've got a number of simple opcodes for pushing individual numbers. You can, I don't know, we've got if and else and things like that in here. So there's conditionals. And again, we'll have a whole other presentation about script and cover all the cool things you can do with that and what the meaning of script is and doing smart contracts on Bitcoin. But the point is that opcodes are individual bytes. So you'll see them in a transaction and they have, this specific encoding for the opcodes. Okay, so a script is a series of operations and data. Scripts have a stack and an alt stack, and there's an example of a script written there as a string, op5, op equal verify. What that script does is push 5 to the stack, push 5 to the stack, and then confirm that they're equal. And if you learn about forth works exactly this way. What I wrote there would be the same thing as running something like, write down like 5 equals, enter. And it says like push 5, confirm that they're equal. That would be true because they are equal. 5 is equal to 5. So that's what the script looks like written in hex. It's op5, op equal verify. Look at what the things that the opcodes from the previous page there, and that's what it looks like. And then there's an example of pushing 2 things to the stack, where this is written in a custom format that's inside the BSV library. What that says is push the following 3 bytes to the stack, 60, 60, 60, hex 60, 60, 60, and then push the same thing to the stack again, and then do op equal verify. So instead of saying is 5 equal to 5, we're saying is this 3-byte value equal to this 3-byte value? And that would also evaluate to true because it is. You can look at it and see it is equal to itself. And then I show what that looks like written in hex at the bottom there. So, okay, now that we've understood all that stuff, we're making progress. This is probably boring a lot of people watching this, but we are filling in all of the bitwise details here to understand everything all the way up to the blockchain. We can now understand what an input in a script is. We've covered everything that you would ever see inside an input. So an input in a script is the hash of the earlier transaction and the output number that it's spending, followed by the length of the script, followed by a script, followed by a sequence number. And the hash is a 32-byte hash value. The output number is a unsigned 32-bit Littleendian integer, which is which output number of the previous transaction is being spent. The script length is a variable-sized Varmint or compact size length number, followed by a script in binary, which is when we cover how to validate a transaction, it is executed actually first, followed by the output of the previous transaction. But anyway, that's what it is in binary, followed by a sequence number. And the original idea of sequence numbers was for payment channels. Payment channels was an idea that Satoshi had going all the way back to the original protocol, where you would update a transaction by iterating the sequence number. And a transaction is considered final if the sequence number is maximum. And then you see an example of casting -1 to an unsigned integer there at the bottom, which I referred to earlier. That's how you get a bunch of like all Fs. When you see transactions written in hex, you'll often see things like this where, there's a 4-byte chunk there that's hex. Well, that's because when you build a transaction normally, if you're not doing a payment channel, you are probably just setting the sequence number to maximum, and that's what it looks like. Yeah, it's a bunch of 1s in binary or a bunch of Fs when written in hexadecimal. And it is a 2's complement number because, again, that's in that particular case, it's like a C++ thing, like it's an integer. And so in summary, so hash, output number, script length, script, sequence number. That's what an input is. And I'm going over this very quickly, but for anybody that wants to look this, you can look at the presentation and think about these things, and all these things do make sense, and that's what it is in detail. Outputs are a little bit simpler. Outputs also have a script in there. It is just a value. So it is a unsigned 64-bit Littleendian number, which is the number of Satoshis that you're sending. So it's interesting. That's the number chosen for the value. And so the number of Satoshis has interesting properties because it maxes out at 21 million. It's not only it's actually not even really a 64-bit number. It actually, I forget what the number of bits is, but you never actually use all 64 because the maximum value is less than that. So anyway, that's how the number is encoded. And then there's also a script, and that's it. So it's just the amount of money that you're sending basically, and a script. So scripts are in the outputs and the inputs. So a transaction looks like this. You have a version number, which is, I said in this presentation, presently 1. We actually have 2 version numbers that I'm aware of live on Bitcoin today. We have 1 and 2. 2 is used if you use a check sequence verify, which is a new opcode. That's a long story. Maybe we'll cover that one in a different presentation. But it's usually 1. You also have the number of inputs, followed by every single input one after the other, followed by the number of outputs, followed by the outputs one after the other, followed by in-lock time. So in this case, the inputs, the number of inputs is a variable size integer. There is, as far as I'm aware, no limit on the number of inputs and no limit on the number of outputs, except that the total size of a transaction cannot be longer than 1 megabyte. So you can have, with that constraint in mind, have any number of inputs and any number of outputs. And then in-lock time says that the transaction is valid until a certain block. And that is usually 0, indicating it's valid originally. So it's always valid. So that's another interesting property of Bitcoin transactions. So, okay, so now that we've done all that stuff, here is an example of a transaction. And I'll just briefly say, like, if you look at the thing on the bottom, a long random string of hex characters, that is a hexadecimal form of a transaction. It's not so easy to interpret that by eye, but you can see things like at the very start of it, there are 4 bytes. That's a Littleendian 1. So that is a version 1 transaction. And at the very end of it, you can see 4 bytes in a row that are all 0. That is the in-lock time. And then inside there, I won't try to describe it, but I can see one place where I see a bunch of Fs. So that is probably I guess it's probably like a sequence number. I guess that must be what that is. I guess. So anyway, I won't spend too much time on that, but note that note now I have the transaction ID is actually the reverse of the hash. So when you hash a transaction, for some reason, they're interpreted as Littleendian numbers. And so when they're then displayed in Bigendian, which has the effect of reversing it. So this is often confusing to people who build wallets, that you hash the transaction with a double SHA-256 hash. Then you have to reverse it when you display it. And if somebody gives you a transaction ID, it is not the hash, it is the reverse of the hash. So bear that in mind, because that trips people up all the time. So here's an example of writing this down in JSON. I won't try to explain all these things. I'll just breeze through this, but know that you can use the library BSV to parse transactions and then look in there. So if you don't want to look at this random looking string of digits here, you can parse a transaction and get a slightly less random looking chunk of stuff here that you can actually read what it says, including like the input hash buffer and all that thing, and see what is in there in a fairly relatively readable way. And here I have, just looking at the one and only input of this example transaction, and you can see it references the hash of the earlier transaction, the output number that is spending, the length of the script. In this case, the script it's relatively simple. You can't quite understand it unless you know what you're looking for, and all it means is push a signature to the stack and then push a public key to the stack. And that's all that this one does. And then the sequence number there is the maximum. So then here's the output. Outputs are simpler. The script is a little bit easier to read because it has actual opcodes in there. And this is a standard script. It's a pub key hash output that it's spending. Let's see, how many is that there? That is 3.3 million Satoshis. So that's like 0.03 Bitcoin. And it's a normal output. And so the hash thing there is actually the hash of a public key. That's an address. And opdupe, op hash 160, followed by the hash, followed by op equal verify op check sig, is what's called a pub key hash transaction output. And that's a standard one. You see this in most transactions, use that as the output. And so in summary, here is the input and output, and we'll discuss all these scripts and other talks about what is, how to execute scripts, how to validate transactions, and things like that. Okay, we've discussed all that stuff, and I know I'm going through here very quickly, but we now understand what can go inside of a block. Blocks contain a bit of metadata in a list of transactions. The block header contains sort of the metadata. It contains the list of the, it contains a hash of the previous block and a Merkle root of the transactions and a couple other things like the time. And so we need to understand what a Merkle tree is. So first of all, let's motivate this by understanding, let's suppose I wanted to download a piece of a file, and I wanted to know that I actually had an accurate piece of the file. You could hash the data one piece at a time and then have the hash of the entire thing, but you would have to download all of the pieces. In this example, I'm just showing a single hash of the entire data. The only way I would know I had the accurate piece would be to download all of the data and then hash the entire thing. So what if we could hash the pieces of data separately so that I could know that if I'm downloading a large file that I've got that one piece correct without necessarily downloading the entire thing. We can hash it in pieces. That scales a little bit better. But there's actually a really good way to do it that scales ideally, which is you put the hashes in a tree. And now what you can do is if you want to download only a piece of the data, you can download what's called the branch of the Merkle tree that's relevant to you. And I now only have to download some of the hashes and only the piece of data that I'm interested in. And this actually scales much, much better. It scales as O log n, where n is the number of pieces of data, which is a very good scaling property. So this is used inside blocks because we want to be able to see, is my transaction in a block without necessarily having to download the entire block. So I simply need my transaction, and then I need the hashes of my own transaction and other hashes around it up the tree all the way to the Merkle root. And then I can download the block headers and see that the Merkle root's in there. And then only this O log n branch of the Merkle tree down to my transaction to see if my transaction's in there without having to download the entire block. So this is useful for SPV nodes because you can validate that your transaction's in a block without actually having to download everything. And the amount of data you have to download is really not that bad at all. It's because it scales as O log n, it's basically your transactions plus some metadata. And so it scales very, very well. You don't have to have that much data to know that your transactions are confirmed without having to download the entire blockchain. Okay, and then here's just another note. I give the exact same note again as before. When you see the hashes of blocks, they are reversed. So if you compute the hash of a block, it will end in a bunch of zeros. But the way that you always see it displayed is that it starts in a number of zeros, because they're interpreted as Littleendian numbers, but they are displayed as Bigendian. So transactions and blocks work the same way in that the hashes are always reversed when displayed. So it's kind of annoying, but that's just how it is. And so be aware of that when you start looking into, transaction hashes and blocks that they are reversed when they are displayed. Now we need to understand something called a target, which is the idea of when I mine Bitcoin, I want to be able to mine a block with a larger number of zeros. And we don't simply look at the number of zeros, we look at something called the target, which gives you, I need to compute a block hash lower than the target. The difficulty, which is actually inside of a transaction, is a floating point number that is the inverse of the target. And it is a 4-byte floating point number. If I wrote that down correctly, it seems like that's kind of small, but I think that's correct. It's like a 4-byte number that's a floating point number indicating the difficulty. And so what miners actually do then is, here's just an example of a hypothetical target. And then when you mine Bitcoin, you need to find a block hash that is lower than this. And you have to, the way you compute the target is by taking the inverse of the difficulty, and which is encoded in bits. And so, yeah, that's mining in the world's briefest possible way. Now we can understand a block header. So inside of a block, we have a block header, which consists of a version, the previous block hash. So there you see the link to the earlier block. You see the Merkle root, which is the root of all the transactions, the Merkle root, followed by the time, followed by bits, or the difficulty, followed by a nonce. And the version byte is currently 2. I don't know if that's still true. I haven't double checked that in several years, but it's probably still 2. The previous block hash of the previous block, Merkle root. The time is a unsigned 32-bit Littleendian number. It is somewhat inaccurate because when miners mine, there's actually, a block is valid if the time is within 2 hours of what the current system time is. So that basically means that miners end up using this as an extra nonce, and you can't actually rely on the time inside of a block. There's something called bits, which is the compact form of the mining target, and the nonce. And the nonce is something that miners can just change randomly so that the hash of everything is different. And so that is a useful tool for the miners to be able to generate different block hashes. And so finally, this is sort of in some ways sort of the conclusion of all this is that this is what a block is. A block is a magic number, which is just always this value, because we transmit them over the network and we want them to start with a number that's just a unique number, followed by the size of the blocks, followed by the block header, followed by the transaction, by the length of the number of transactions, followed by the list of transactions. And that's it. That's what a block is. And so the blockchain is a bunch of those. And so in summary, we've now covered everything leading all the way up here. And so obviously this was very fast and probably almost no one is capable of remembering everything we talked about. But we did cover literally every single format inside of the blockchain. So if you understand everything in this presentation, you understand every single bit and byte that is actually inside of transactions and blocks in the blockchain. So in summary, what they are is, well, a block contains transactions. Transactions have inputs and outputs. The input of a transaction always links to an earlier output. Blocks, which contain transactions, also link to the earlier block. And so you can trace the blockchain all the way back to the Genesis block. That is the first block. And each transaction, you can trace the inputs all the way back to a Coinbase transaction. Each block has a Coinbase transaction, which are where new Bitcoin comes from. So Coinbase transactions are the mining reward inside blocks. So they do not link to earlier transactions. And the Genesis block doesn't link to an earlier block. And other than that, all the transactions that you deal with link to earlier ones, and all blocks that you deal with link to earlier ones. So that's it in a nutshell. Now, these are homework assignments for all the people watching this if you want to really prove that you understand this. These are just examples of things you can do if you want to understand all these things. So you can try converting numbers into Bigendian, Littleendian, sign magnitude, two's complement, and see the results so that you yourself, and you can easily do this in Node.js, actually, or C++ if you wanted to, but it's way easier in Node.js. You can also do things like, okay, use a library to find a recent transaction and hash it yourself and confirm that you get the correct hash. And note that things are always displayed in reverse. So to validate it, you will have to actually reverse it. Then another thing is using standard libraries, parse a transaction and a block and spit out the structure in JSON. So you can do this using BSV, our library. You can input transactions and blocks and then spit them out in JSON and just see what data you get, and you can look at it and analyze it and so on. Using a standard library, build a Merkle tree and confirm that you get the Merkle tree correct. Now you have to know some details about exactly how things are hashed, which you can easily see inside of, you look at the source code of the library. And then finally, if you understand mining, you can mine the statement money button by appending a nonce to the sentence and then changing the nonce until you find a hash that starts with at least 1 0. And that's what Bitcoin miners do. Okay, so that was super fast overview of all of the details of what is inside transactions and blocks. And now is probably a good time if you guys have comments or questions. I know that it was super fast and covered so much, but if we did questions in the middle, it would probably take really long.
Well, first of all, the comment that always appear with this, right? That is like, how cool is that you can just use BSV, the library, and forget about this almost all the time, right? Because
yes,
it's really hard if you have to think, oh, which is the order of the numbers, or where I have to think if this is a 64 bytes or 128 byte number. With this, you just use BSV. You have big numbers inside. Everything's formatted as it has to be. And in most of the cases, you can just use money button, creating a really high level language, the transactions, and you don't have to think about all of this. But it's really cool to understand what is going on the blockchain and like under the hood, right?
Yeah. So yes, certainly. Hopefully, most people do not have to. This is kind of like. Hopefully, this will become one of those things where basically only the node developers will actually know most of these details. It's probably hopefully how this happens. Basically, if you're actually working on the C++ code inside of a node, should you really understand every single one of these things. And it's as you say, like using BSV, the library, and of course money button. Most of these are abstracted away from you already, and the developer can do things like make an app where people can send money and accept payments and post data to the blockchain without actually understanding any of these things at all. That you can just plug money button in and start doing these things. So yes.
Yeah, that's really cool. So regarding like all the presentation, I have two comments. Mm-hmm. One is for the less technical users. You mentioned proof of work a lot, and maybe there are some users that doesn't really know what it's proof of work. So maybe we can just make a presentation about that. And the second one is a more technical level. That is how can I choose outputs and inputs on a transaction if I want to use one like the terminal output or input. And I've just commented that because we actually speak about it previously, and I think it's kind of cool that we can share that information with in this training program.
Yeah, so on the presentation thing, so doing proof of work, so probably what we should do is there could probably be a presentation on mining is probably the way to do that. And I don't know if any of these people happen to be watching, but it would be cool to interview Steve Shatters, wink, wink, if he happens to watch this or somebody tells him that. Either him or somebody who knows about that type of thing that can talk about mining, and we can cover that. There should also probably just be a generic overview, like what the hell is Bitcoin? Because if people don't know what is Bitcoin, they listen to everything I just said, they're going to have no idea what I'm talking about, and they're going to zone out after 1 minute. But if we had a general overview that it can explain some technical things, like what is mining, without going into anywhere near this level of detail, so that those people can understand. Yeah. And
regarding the other question, like how like you mentioned, Ryan, that basically you have transactions linked to each other, right? You have inputs that consume outputs, basically, and it says how people select what outputs they are spending, basically. Basically, you have the outputs that you have, the system that we call UTXOs all the time, are outputs that are not expended by another input, and that you own the private key to make the signature, basically. So those are the ones that are your outputs that you can spend on the network. So that's basically, I can spend a Ryan output because I don't have the private key to make the signature and actually expand it, basically.
And this is one of those things that wallets are doing under the hood that most people, even people that are involved in Bitcoin, often don't understand these things. But what your wallet says is, you have X number of Bitcoin. What it's really doing is it says, I have access to in UTXOs. And if I add up the value in each UTXO, it adds up to be X number of Bitcoin. It's already simplifying things. And when you go to spend the Bitcoin, your wallet has to choose enough inputs, or sorry, it has to choose enough outputs to put into inputs so that you have enough money to pay the amount of money that you want to spend and send the rest back to you as change. So there's something called a UTXO selection strategy that every wallet does, and they often do it differently. But the wallet is doing that automatically. It builds a transaction for you without you having to worry about, but what are the inputs? Well, you don't have to think about it. The wallet just builds it, and it picks some for you. It picks some of your unspent outputs. And this matters just because there are all sorts of things wallets don't yet do, but they could do to have cool properties. Like we've had to worry about this with Money Button, where, well, one of the things that we care about is making sure that you don't run into this 25 unconfirmed transaction chain limit. So the way our UTXO selection strategy works at present is we always spend the oldest UTXOs first, because those are the ones most likely to be confirmed. This means that most of the time when you go to send money, it works. But there are cases which basically, if you're uploading a large file, where you notice that, oh, sometimes it stops working and you have to do other things that are complicated. And there are all sorts of advanced things we can do to make this better, involving more sophisticated UTXO building and selection strategies. Things like privacy matter too, because anytime you build a transaction that spends all of your UTXOs, you are revealing that you own all of those, and all of that data goes on the blockchain. So there are privacy implications to the way that you do, what is your UTXO selection strategy. So that's one of those things where, like, basically, wallet builders have to be aware of these things. And what properties do you care about? Do you care about speed? Do you care about privacy? Do you care about expense? All these things matter. And this is something that wallets normally do under the hood. But an advanced wallet could actually allow the user to do these things if they wanted to. Like, you could imagine building an advanced wallet that showed you what your UTXOs are and could group them according to which ones have been revealed as having you as the owner. You could even have like different groups that are different, that you could spend on different things if you wanted to. So you could have, whatever, like, I don't know, anything that you cared about privacy and not linking together your funds from your earning from a company with the funds from some other place or something like that. You could do things like that and refuse to mix them. So anyway, all that will come over time, but this is how, for anybody building a wallet, these things do matter, because it's the only way you're going to have a wallet with good privacy is if you understand what these things mean.
Yeah. And also regarding, because you comment the limit transaction error, there's a really cool blog post that we post on our blog that explain how the error limit transaction work and how you can solve it. So we can link our users to that post also.
Yes, good idea. We'll definitely do that. Okay. I don't know how long was this one. This one, I think this is probably about an hour, I think.
Yeah, probably the longest one until now.
Okay. So this one, so this was super technical, but the thing is, anybody that actually at any point needs to understand any of these technical details can refer to this, and we covered everything. Every single bit inside of what is a transaction on the block is in this video, and you now can have a reference for all that information. So we'll now proceed to other things that are a little bit higher level, like how do I actually build a transaction and stuff like that. And then, of course, the theme in all this is that we're solving almost all of these inside money buttons so that most apps do not need to actually know almost any of this, that basically most of the time you can just plug money button into your app and it will just work without actually having to know any of these things. All right, anything else, guys? Or I can close it out with our usual references to our website and stuff. So go ahead.
No, just that. I believe we are set. You can close the video.
Okay, so please visit us at moneybutton.com. Our documentation is at docs.moneybutton.com, where you can see all these articles and videos that we're creating about all this information. We have a blog where we are putting sort of articles about these things. So that's blog.moneybutton.com. And we're grouping all of these videos and articles into sections. So if you want to understand different parts, you can look at that section. So this video will be the first one in the section on transactions and blocks. And the other sections are things like keys and signatures and basic technical things, technical preliminaries. We'll probably have more advanced things later on, or higher level things and different subjects even, when we invite other people to talk about things, other things that matter, like the economics and the law of Bitcoin. We'll cover that stuff as well. So we're grouping all of these things together. That's on our blog, blog.moneybutton.com. And if you have any questions or comments about any of this stuff or need help building anything, please join us in our Telegram group. That's where we're sort of doing all of our talking with users and stuff. Largely happens there. Maybe not mostly, but we're trying to get it to happen there. That's t.me/moneybuttonhelp, our Telegram group where you can talk with us. So that's it. So thank you everyone for watching, and hopefully everyone sticks around, and we'll have more videos and more articles almost every day.
Awesome.
All right, see you guys.